Hello, this is Joe. If you have learned the lesson, The Nth Roots of Unity, I hope this video will make you more clear about it. Before the next 4 exercises, we do some review. Essentially, the knowledge behind the exercises is more important. First of all, you should know the definition. In other words, z is the root of this polynomial. And since 1 is definitely one of the roots, so we can extract the factor x minus 1 from the x to the nth power minus 1. And what it left is a GP. So this expression is important. And in the complex field, 1 could be described in 1 plus I0 and equals to this form. According to Euler's identity, we can get this form. So if we write the nth root of the unity into this form, and we can get z is equal to this. And this expression is the tool to deal with our exercises. Moreover, if we set omega equals to cosine 2 pi over n plus I sine 2 pi over n. And according to De Morville's theory and the tool, we can get that all the roots could described by omega's power. And on the complex plane, the nth root of unity divides the unit circle into a n equal x of 2 pi over n radians. We could take cube roots of unity as an example. The first root is 1, and at this point, rotate 2 pi over 3 radians to the second one, and this is cosine 2 pi over 3 plus I sine 2 pi over 3. That means negative square root 3 over 2 plus square root 3 over 2i. And another 2 pi over 3, we get the third one, and that is negative square root 3 over 2 minus square root 3 over 2i. According to just mentioned about this, we could see omega equals to 1 minus square root 3 over 2 plus square root over 2i, or negative square root over 2 minus square root over 2i. And if omega equals to 1 and a, the result obviously is 2, b, the expression is 4 times 4 means 16, and for the last one means 1 plus 3 plus 1 cube means 5 cube means 5 times 25, that means 125. If omega is not equal to 1, to substitute directly is not a smart choice. We could see omega's cube equals to 1, and omega cube minus 1 equals to omega minus 1, omega square plus omega plus 1 equals to 0. So we can get another form that omega square plus omega plus 1 equals to 0. That means for a, we can extract omega to the 10th power from each term, so we get 1 plus omega. And according to this form, 1 plus omega equals to negative omega square, and we can get omega to 10th power times negative omega square. That means negative omega to the 12th power. It's omega cubed to the 4th power. That means minus 1. The second one, we can expand it, and it will be 1 plus 3 omega squared plus 3 omega plus 9 omega cubed. That is a constant, so we can get 10 plus 3 omega squared plus omega. That means minus 1, so it's equals to 7. For the third one, we can see 1 plus omega squared, and still we have 2 omegas and cube. That means 0, and this expression means 2 omega squared. That means 2 squared times omega squared. That means 8 times 1. That is 8. Exercise 2. Write the roots of the equations in form of a plus bi. First of all, and we can use the tool. That means 2k pi over 4i equals to cosine k pi over 2 plus I sine k pi over 2, and k is equal to 0, 1, 2, 3, and if k is 0, that means cosine 0 plus I sine 0 is equal to 1. The second one is cosine pi over 2 plus I sine pi over 2 equals to I. The third one is cosine pi plus I sine pi equals to minus 1. The last one is cosine 3 pi over 2 plus I sine 3 pi over 2 is equal to negative I. But for this problem, we could choose another strategy, factorization, because 4 is too special. Z squared minus 1, Z squared plus 1. That is Z plus 1, Z minus 1, times Z plus I times Z minus I. That means Z could be minus 1, positive 1, and negative I, positive I. Next one is boy. Z to the 5th power is equal to 1. Again, use the tool, 2k pi over 5, and that equals to cosine 2k pi over 5 plus I sine 2k pi over 5. K is 0, 1, 2, 3, 4. Then we can get these roots. The first one is 1. Second one is cosine 2 pi over 5 plus I sine 2 pi over 5. The third one is cosine 4 pi over 5 plus I sine 4 pi over 5. Next one. Each time the angle will increase 2 pi over 5. I sine 6 pi over 5. The last one is cosine 8 pi over 5 plus I sine 8 pi over 5. If you want to do some simplification, that means minus cosine pi over 5 plus I sine pi over 5. This one is minus cosine pi over 5 minus I sine pi over 5. The last one is cosine 2 pi over 5 minus I sine 2 pi over 5. Look at the last one, C. And the right of the equation is 32, different from A and B, so we can do some change. Z to the fifth power equals to 32 means 2 to the fifth power. And we're familiar with 1, so we can divide the equation with 32. That means Z over 2 to the fifth power equals to 1. And we can set U is Z over 2. That means U to the fifth is equal to 1. And this problem is exactly the same with the problem boy. So the result of this, Z is equal to 2U, and U is exactly the same as the second one. So the result is 2, second one is 2 times 2 pi over 5 plus I2 times sine 2 pi over 5. Third one is negative 2 times cosine pi over 5 plus I2 times sine pi over 5. Fourth one, negative 2 times cosine pi over 5 minus I2 times sine pi over 5. Last one is 2 times cosine 2 pi over 5 minus I2 times sine 2 pi over 5. Exercise 3 solves the equation. If you remember what we mentioned in the beginning, we can multiply z minus 1 on both sides of the equation. Z to the fourth power, z cube, z square, z plus 1 equals to 0. That means z to the fifth power minus 1 equals to 0. Such that z to the fourth power, z cube, z square plus z plus 1 is equal to z to the fifth power minus 1 over z minus 1. And of course, you can see z square, z cube, z to the fourth power. And this sequence is a GP with the first term 1 and common radius z. So 1 plus z square, z cube, z to the fourth power. That means 1 minus z, and the numerator is 1 minus z to the fourth power times common radius. That means z to the fifth power minus 1 over z minus 1. And this one and this one is the same. So you can choose 1 or you can choose 2. So we can see the exact problem. What we have to do is to solve z to the fifth power minus 1 equals to 0 and z is not equals to 1. That means we have to deal with the fifth roots of the unity, and we don't want the 1. And this equation we have solved in exercises 2, so the next step is clear. If you want to simplify, look at the last problem, and this sequence is 1 negative 2 times z, 4z square. That means negative 2z square. And the last one is negative 8z cube. We can describe it with this. So this is GP with first term 1 and common radio -2 times z, and the sum of this sequence is 1 minus common radio first term minus last term times common radio. So the problem we can describe as this way. So -2 times z to the fourth power equal to 1 and -2z not equal to 1. And here we choose that we have mentioned about. We could set -2 times z is u, and the sum of the sequence we can describe in 1 plus u squared plus u cubed is equal to 0. And according to the exercise 3, we can describe that. So u to the fourth power equal to 1 and u is not equal to 1. And we have known exactly about the 4 roots through the exercise 2, and we not need the 1, so u could be -1i and -i. Since z is -half u, so the result is z could be half, and -half I or half I. That's all. Thank you for your watching. Thank you.